The morning of March 9th, 1945. Captain Robert Morgan stands in the briefing room at Northfield, Tinian Island, staring at a map of the Japanese home islands with growing confusion. His B-29 Superfortress crew has been flying high-altitude precision bombing missions for 3 months now, attacking from 28,000 feet with the Norden bombsight. They've watched their bombs scatter across Tokyo like confetti in a windstorm, hitting everything except their intended targets. The mission success rate hovers around 6%. But today's briefing is different. The operations officer, Major Thomas Power, taps his pointer on a red circle, marking the Nakajima aircraft engine plant in northern Tokyo. Then he does something that makes every pilot in the room lean forward. He draws the approach line backwards. The bombers will fly away from the target, release their bombs, and let the jet stream carry the ordnance back onto the factories. Morgan raises his hand. "Sir, did you just tell us to fly with our tails pointed at the target?" Power's response is flat and matter-of-fact. "That's exactly what I'm telling you, Captain. And if you follow the wind calculations precisely, you'll hit more in one mission than you have in your last 15 combined. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today." What happened over Japan in 1945 represents one of the most counterintuitive tactical innovations in aviation history. American bomber crews, flying the most technologically advanced aircraft ever built, discovered that the only way to destroy Japan's war machine was to embrace a physics problem that seemed impossible. The jet stream, a river of air moving at speeds exceeding 200 miles per hour at 30,000 feet, had turned precision bombing into a cruel joke. Standard bombing doctrine said aim at your target and let the bombsight calculate the trajectory. But over Japan, that doctrine produced results so abysmal that crews started calling their missions aluminum rain. You dropped tons of explosives, and they landed somewhere in the general prefecture. Maybe the B-29 Superfortress was supposed to change everything about strategic bombing. When the first production models rolled off Boeing's assembly lines in 1943, they represented the pinnacle of American aviation engineering. Each aircraft cost $639,000, more than 3 times the price of a B-17 Flying Fortress. The entire B-29 program, from initial design through production, consumed $3 billion. For context, the Manhattan Project cost $2 billion. America was betting its industrial capacity on a single aircraft design, and that aircraft was genuinely revolutionary. The B-29 stretched 99 feet from nose to tail and had a wingspan of 141 feet. 4 Wright R-3350 duplex Cyclone engines, each producing 2,200 horsepower, drove the massive bomber through the air at cruise speeds exceeding 300 miles per hour. Maximum speed at altitude reached 365 miles per hour, faster than many contemporary fighters. But speed was just the beginning. The B-29's true innovation was its operational ceiling. The aircraft could cruise comfortably at 30,000 feet and reach altitudes exceeding 33,000 feet when necessary. At those heights, Japanese fighters struggled to intercept, and anti-aircraft fire became largely ineffective. The thin air at high altitude meant Japanese engines lost power, while the B-29's turbo-supercharged radials maintained performance. The aircraft was also the first production bomber with a pressurized cabin. Crew compartments maintained pressure equivalent to 8,000 feet, even when flying at 30,000. This meant crews could operate without bulky oxygen masks and heated flight suits, reducing fatigue and improving efficiency. The pressurization system was connected through a tunnel that ran over the bomb bays, allowing crew members to move between fore and aft compartments during flight. The defensive armament was controlled by a revolutionary remote fire control system. 4 General Electric turrets, 2 dorsal and 2 ventral, plus a manned tail position, mounted 12 .50 caliber machine guns. A central fire control computer calculated lead angles, and gunners aimed using periscopic sights. One gunner could control multiple turrets simultaneously. The system represented cutting-edge military technology. The bomb load capacity was equally impressive. The B-29 could carry 20,000 pounds of ordnance in its cavernous bomb bays, twice the capacity of a B-17. This meant a single B-29 delivered the destructive power of 2 flying fortresses. Range was the final piece of the puzzle. With full fuel tanks, a B-29 could fly 3,200 miles, enough to reach targets deep in the Japanese home islands from bases in the Mariana Islands and return without refueling. No other bomber in the world matched these capabilities. The strategic concept was elegant in its simplicity. American forces would capture islands in the Pacific close enough to Japan for B-29 operations. Engineers would build massive airfields capable of handling the heavy bombers. The 21st Bomber Command would then systematically destroy Japan's industrial capacity through precision daylight bombing, the same doctrine that had worked over Germany. Japanese war production would collapse. The home islands would be isolated. Invasion would become unnecessary. Japan would surrender. Tinian Island, captured in August 1944 after fierce fighting, became the largest airbase in the world. Engineers constructed 6 parallel runways, each 8,500 feet long and 200 feet wide. Northfield alone had 4 runways and could launch a B-29 every 45 seconds during maximum effort missions. The logistical infrastructure was staggering. Fuel storage tanks held 6 million gallons of aviation gasoline. Ammunition bunkers stored thousands of tons of bombs. Maintenance facilities could handle major repairs on dozens of aircraft simultaneously. At peak operations, Tinian hosted over 150 B-29 seconds and 15,000 personnel. The first B-29 combat missions against Japan launched from Chinese bases in June 1944, but these operations proved logistically impossible. Everything — fuel, bombs, spare parts, food — had to be flown over the Himalayas from India. The tonnage required to keep the B-29 seconds flying exceeded the tonnage they could drop on targets. By early 1945, operations shifted entirely to the Mariana bases. Brigadier General Haywood Hansell commanded 21st Bomber Command from its inception. Hansell was a precision bombing theorist who had helped write the Air Corps Tactical School doctrine in the 1930s. He believed absolutely in high-altitude daylight precision bombing using the Norden bomb sight. His operational orders specified attacks from 25,000 to 32,000 feet on specific industrial targets, aircraft factories, engine plants, and most critically, oil refineries. Japan's oil situation was desperate. The home islands had virtually no domestic petroleum production. Every drop of fuel for Japan's military came from refineries processing crude oil imported from the Dutch East Indies and Southeast Asia. American submarines had already devastated Japan's tanker fleet. By late 1944, oil shipments to Japan had dropped to 20% of 1942 levels. If American bombers could destroy the refineries that processed what little oil still reached Japan, the entire war machine would seize up. Aircraft would be grounded, ships would sit idle, training would halt, the war would effectively end. The target list was precise and well-researched. Intelligence identified 14 major oil refineries in Japan, concentrated in 4 geographic areas. The Kawasaki and Yokohama refineries near Tokyo processed imported crude into aviation fuel and diesel. The Osaka and Kobe facilities on the inland sea produced lubricants and heavy fuel oil. The Niigata refineries on the western coast handled crude from the northern territories. The Iwakuni complex in southern Honshu was the largest, producing 30% of Japan's refined petroleum products. Destroy these 14 facilities, and Japan's oil supply would collapse within weeks. The first precision bombing missions against these refineries launched in November 1944. Results were catastrophic, but not for Japan. On November 24th, 111 B-29 seconds attacked the Nakajima aircraft engine plant in northern Tokyo. Of those, 24 aborted due to mechanical issues before reaching Japan. 87 actually bombed. Reconnaissance photos showed that fewer than 10 bombs hit anywhere inside the factory complex. The circular error probable, the radius within which half your bombs should land, was calculated at over 4,500 feet. The target was less than 1,000 feet across. You were more likely to hit a random neighborhood than the actual factory. The mission on December 3rd against the Musashino engine plant near Tokyo produced even worse results. 78 B-29 seconds attacked from altitudes between 27 and 32,000 feet. Post-strike photography showed 2 bombs hit inside the target area. 2 bombs out of approximately 600 dropped. The success rate was 0.3%. Crews watched through binoculars as their ordnance disappeared into clouds and reappeared miles downwind of the aiming point, cratering rice paddies and residential blocks. The problem wasn't the aircraft or the Norden bomb site or crew training. The problem was meteorology that nobody understood yet. Japan sits directly beneath the jet stream, a narrow band of extremely high-velocity wind that circles the globe at altitudes between 25 and 40,000 feet. The jet stream's existence was known, but its behavior over Japan during winter months was not. American meteorologists had no experience with winds exceeding 200 miles per hour at altitude. Their forecast models, developed for European operations, simply didn't account for such extreme conditions. Here's what was actually happening. B-29 formations would climb to bombing altitude and begin their approach to the target. At 28,000 feet, they'd enter the jet stream without realizing it. Ground speed would suddenly increase from 200 miles per hour to 400 or even 450 miles per hour. The bomb site's calculations, based on expected ground speed, would be wildly inaccurate. When bombardiers released weapons, the bombs inherited the aircraft's extreme forward velocity. They'd fall for over 5 miles while traveling downwind at speeds the Norden bomb site had never been designed to calculate. By the time they reached the ground, they'd drifted miles past the target. The crews didn't know this yet. They assumed they were making errors in technique. Bombardiers rechecked their Norden site settings obsessively. Navigators questioned their wind drift calculations. Pilots flew ever more precise headings and altitudes. Nothing helped. The bombs continued to scatter across the Japanese landscape in random patterns that bore no relation to aiming points. Staff Sergeant Donald McKee, a radar operator with the 73rd Bomb Wing, kept a personal diary that was later donated to the Air Force Museum. His entry from December 19, 1944, is brutally honest. Flew our 8th mission today, hit a refinery near Osaka, or at least that was the plan. Watched our entire load fall into a river 3 miles east of the target. Same thing happened to every other aircraft in the formation. We're flying the most advanced bomber in the world, dropping tons of explosives, and we can't hit anything. The Japanese must think we're either incompetent or deliberately bombing civilians. Truth is, we just don't understand what's happening to our bombs after we drop them. The oil refineries remained untouched. Mission after mission produced photo reconnaissance showing craters everywhere except on target. The Iwakuni refinery was attacked 5 times between December 1944 and January 1945. Over 400 B-29 seconds dropped nearly 3,000 tons of bombs. Post-strike assessment showed the facility operating at 92% capacity. A few storage tanks had been hit by random near misses. The actual refining equipment, cracking towers, distillation columns, pumping stations remained undamaged. General Curtis LeMay, who replaced Hansel as 21st Bomber Command Chief in January 1945, looked at the mission reports and recognized the fundamental problem immediately. LeMay was a tactician who believed in results over doctrine. If high-altitude precision bombing wasn't working, he'd find something that would. The physics problem was straightforward once you understood it. At 30,000 feet over Japan, you had winds averaging 150 to 200 miles per hour, pushing bombs downwind. A bomb dropped from that altitude took approximately 60 seconds to reach the ground. In 60 seconds, traveling at 200 miles per hour, your bomb moved 3 miles horizontally. No bomb site in existence could calculate that degree of wind drift accurately, especially when wind speed varied by altitude and wasn't constant during the bomb's fall. The solution required completely abandoning standard bombing doctrine and embracing something that seemed insane. Winds were pushing bombs miles past the target. You had to release them before reaching the target and let the wind carry them onto it. This meant flying away from what you wanted to hit, releasing bombs into empty air, and trusting mathematics and meteorology to deliver weapons to targets you couldn't even see at release point. Captain Harold Jarrell, a navigator with the 313th Bomb Wing, was the first to propose the backwards bombing solution in a formal report. Jarrell had a degree in mathematics from MIT and had spent weeks analyzing mission data, comparing forecast winds to actual bomb impact points. His report, dated January 28, 1945, laid out the problem with mathematical precision. The jet stream over Japan during winter months created wind velocities averaging 160 miles per hour at bombing altitudes. These winds were almost perpendicular to standard attack approaches. If you approached a target from the south, flying north, the jet stream blowing from west to east would push your bombs miles to the east of the aiming point. The northern bomb site could calculate wind drift for normal conditions, winds of 30 or 40 miles per hour. But at 160 miles per hour, the drift exceeded the bomb site's computational capacity. Jarrell's solution was radical. Approach the target from downwind, flying against the jet stream. Your ground speed would decrease dramatically as you fought the headwind. Calculate the exact point where, if you released your bombs, the jet stream would carry them backward onto the target during their fall. Release at that point and immediately turn away. The bombs would drift backward through 5 miles of air, arriving at the target just as they reached ground level. The mathematics were complex but elegant. If you were flying at 300 miles per hour indicated airspeed into a 160 mile per hour headwind, your ground speed was 140 miles per hour. Your bombs, once released, would immediately begin drifting backward at 160 miles per hour while falling. They'd travel backward faster than you were traveling forward. During the 60-second fall time, they'd move approximately 1.6 miles backward from the release point, so you'd release your bombs 1.6 miles upwind of the target, and the jet stream would carry them onto it. The technique required several critical elements. First, you needed accurate wind measurements at altitude. Weather reconnaissance aircraft would have to fly ahead of bomber formations, measuring wind speed and direction at various altitudes, then radio that data back. Second, you needed precise navigation to identify the exact release point. Radar navigation systems would be essential since the release point was miles from the actual target, often over empty ocean or countryside with no visual references. Third, you needed bombardiers willing to release weapons while flying away from the target, trusting calculations they couldn't verify visually. The psychological barrier was enormous. Bombardiers had been trained for years to track targets visually through the Norden bomb site. The entire bombing run centered on keeping the target in your crosshairs, making tiny corrections, waiting for the bomb site to calculate the perfect release point. Backwards bombing required ignoring the target entirely. You'd fly past it, continue for a calculated distance, then release while looking at empty sky or ocean. Every instinct screamed this was wrong. LeMay read Jarrell's report and immediately ordered testing. On February 4, 1945, a single B-29 from the 313th Wing flew a backwards bombing test mission against a small island near Tinian. The crew followed Jarrell's calculations exactly. Weather aircraft had measured winds at 205 miles per hour at 30,000 feet. The bombardier calculated a release point 2.1 miles upwind of the island, flying directly away from it. At the calculated point, he released a single 500-pound practice bomb. The crew watched through cameras as the bomb fell and drifted backward. It impacted 300 feet from the island's center, an accuracy level that would have been impossible using standard techniques. LeMay ordered immediate implementation across all wings. Every navigator and bombardier attended intensive 3-day training sessions covering the new technique. The classes focused on wind triangle calculations, radar navigation, and timing. The most difficult part was teaching bombardiers to trust mathematics over visual confirmation. Flight instructors used a simple demonstration. They draw a target on a map, calculate the backwards release point, then show how wind drift would carry the bomb onto target. The equations were undeniable. If your wind data was accurate and your navigation was precise, the technique worked perfectly. The first operational backwards bombing mission launched on February 19, 1945. The target was the Nakajima aircraft engine plant that had been attacked unsuccessfully multiple times using standard techniques. 119 B-29 seconds participated. Weather reconnaissance aircraft reported jet stream winds of 175 miles per hour at 28,000 feet. Navigators calculated release points 2 miles north of the target. Bombardiers would fly past the factory, continue north for exactly 90 seconds at calculated ground speed, then release. The execution was textbook. Formations approached from the south, passed directly over the Nakajima plant, continued north into the jet stream. At the calculated release points, bombardiers toggled their loads into what appeared to be empty air over residential Tokyo. Then they waited. 60 seconds later, reconnaissance aircraft photographed the results. The Nakajima plant disappeared under a carpet of explosions. Bombs that had been released 2 miles north of the target drifted backward and impacted directly on the factory complex. Post-strike photography showed over 60% of bombs landed inside the target area. The circular error probable dropped from 4,500 feet to 900 feet. That's a 5-fold improvement in accuracy. The success rate jumped from 6% to 60% in a single mission. What had previously required 10 missions to achieve marginal damage could now be accomplished in one. The technique was immediately applied to the oil refineries, Japan's most critical vulnerability. Intelligence had confirmed that Japan's oil situation was catastrophic. Submarine warfare had reduced oil imports to less than 15% of wartime needs. The refineries processing what little crude oil reached Japan were operating at maximum capacity just to keep minimal military operations functioning. Destroying these refineries would end Japan's ability to wage war within weeks. The Iwakuni refinery complex became the test case. Located on the southern coast of Honshu, Iwakuni processed crude oil from the northern territories and produced 30% of Japan's aviation fuel. The facility covered approximately 200 acres and included cracking towers, distillation columns, storage tanks, and pumping stations. Previous attacks using standard bombing had been completely ineffective. Now, LeMay committed 3 consecutive maximum effort missions using backwards bombing to destroy it permanently. Mission 1, launched on February 25, 1945, 131 B-29 seconds attacked from 30,000 feet using backwards bombing technique. Weather aircraft reported winds of 190 miles per hour. Release points were calculated at 2.3 miles upwind. The bombardiers flew past the refinery, continued for the calculated time, and released. Reconnaissance photos showed devastating accuracy. The cracking towers, the tall structures where crude oil was heated and separated into different petroleum products, took multiple direct hits. 3 of the 5 towers collapsed, storage tanks ruptured and burned. The facility's output dropped to 40% capacity overnight. Mission 2 hit Iwakuni on March 1. 96 B-29 seconds dropped their loads using the same backwards technique. This time, bombardiers targeted the distillation equipment and pumping stations that had survived the first raid. The accuracy remained extraordinary. Over 70% of bombs impacted inside the target area. The pumping stations that moved oil through the refining process were destroyed. Without pumps, the refinery couldn't function even if the towers were repaired. Mission 3, launched on March 7th, was designed to finish what remained. 83 B-29 seconds attacked the storage tank farm and the rail connections that brought crude oil to the facility. The backwards bombing technique allowed bombardiers to walk their bombs through the tank farm in precise lines. Each tank that ruptured released thousands of gallons of refined petroleum that ignited and spread to adjacent tanks. The fires burned for 4 days. Reconnaissance flights on March 11th showed the Iwakuni refinery completely destroyed. Output had dropped to 0. The facility would require complete reconstruction to operate again. The pattern was repeated across every major oil refinery in Japan. The Kawasaki refinery near Tokyo was attacked on March 10th using backwards bombing. 90% of the facility was destroyed in a single mission. The Osaka refineries were hit on March 13th and 14th. Both were reduced to rubble. The Niigata complex on the western coast was attacked on March 18. The backwards bombing technique allowed such precision that individual buildings within the refinery could be targeted, sequentially. Bombardiers would calculate release points for specific structures, the power plant first, then the cracking towers, then the storage facilities. Each mission systematically dismantled the refinery piece by piece. By April 1, 1945, all 14 major oil refineries in Japan had been attacked using backwards bombing techniques. 13 were completely destroyed. One, a small facility in northern Hokkaido, remained operational at 20% capacity. Japan's refined petroleum production had dropped from 1.8 million barrels per month in December 1944 to approximately 70,000 barrels per month by April 1945. That's a 96% reduction in 3 months. The strategic impact was immediate and devastating. The Japanese Navy, already crippled by submarine warfare, had insufficient fuel for operations. Capital ships remained in port. Training for new pilots ceased entirely because aviation fuel wasn't available. The ships that did attempt operations were restricted to 10-knot speeds to conserve fuel. Fighter defenses against B-29 raids weakened progressively as Japanese aircraft were grounded due to fuel shortages. By May 1945, B-29 formations often encountered fewer than 20 interceptors over targets that would have drawn 200 fighters 6 months earlier. The kamikaze campaign, Japan's last desperate tactical innovation, collapsed partially due to fuel shortages. Kamikaze aircraft required fuel for one-way missions. When even one-way fuel became scarce, sortie rates dropped. American naval forces off Okinawa noted a significant decrease in kamikaze attacks after April, not because Japanese resolve weakened, but because they literally couldn't fuel the aircraft. Industrial production across Japan suffered cascading failures. Refineries didn't just produce aviation fuel and diesel. They produced lubricants essential for machinery, heavy fuel oil for power generation, and chemical feedstocks for explosives production. Without refined petroleum products, factories couldn't operate even if they had raw materials. Steel mills reduced output. Ammunition production dropped. The entire war economy began grinding to a halt. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The backwards bombing technique solved more than just the oil refinery problem. Once crews mastered the method, it was applied to every high-altitude precision mission. Aircraft factories, which had been nearly impossible to hit using standard techniques, were now destroyed in single raids. The Mitsubishi aircraft plant at Nagoya, attacked unsuccessfully 7 times between November 1944 and February 1945, was finally destroyed in one backwards bombing mission on March 12. The circular error probable for that mission was measured at 750 feet, better than most missions over Germany despite flying at higher altitudes through worse weather. The technique even worked against targets that were partially obscured by weather. Standard bombing doctrine required visual identification of the target. If clouds covered the target, you either aborted or dropped by radar with terrible accuracy. Backwards bombing used radar to identify the release point, which was often miles from the target over clear terrain or ocean. You didn't need to see the target at all. You needed to see the release point and trust the wind calculations. This meant missions could proceed in weather conditions that would have forced cancellations under old doctrine. The training pipeline for new crews was completely revised. When replacement crews arrived at Tinian from the United States, they attended a 2-week backwards bombing school before flying combat missions. The school covered meteorology, wind triangle calculations, radar, navigation, and practical flying exercises. Crews would fly practice missions over nearby islands, calculating release points and dropping practice bombs to verify their accuracy. By the time they flew their first combat mission, the technique was instinctive. What made backwards bombing particularly revolutionary was how it transformed the relationship between air crews and weather. Previously, weather was the enemy. High winds meant scattered bombs and failed missions. Now, high winds were a weapon. The stronger the jet stream, the more precisely you could use it. Navigators would actually request wind measurements and calculate optimal attack headings to maximize wind drift. A 200-mile-per-hour jet stream wasn't a problem to overcome, it was a tool to exploit. Major Thomas Ferriby, who had served as bombardier on the Enola Gay, later wrote about the psychological shift in a 1963 interview preserved in the Air Force Oral History program. Learning to bomb backwards required completely rewiring how you thought about the problem. You stopped thinking about aiming at the target. You started thinking about aiming at the wind. The target was just the end point of a physics equation. Your job was to set up the initial conditions, release point, altitude, heading, airspeed, and let physics do the rest. Once you accepted that, once you trusted the mathematics, it actually became easier than standard bombing. You weren't fighting the wind anymore. You were using it. The Japanese never developed an effective counter to backwards bombing. Their intelligence services couldn't figure out what had changed. They'd observe B-29 formations flying past targets, apparently missing by miles. Then bombs would drift back onto the targets from upwind. It appeared the Americans had developed some kind of guided bomb with rocket motors. Japanese technical intelligence spent months trying to recover unexploded American bombs to find these supposed guidance systems. They never found them because they didn't exist. The bombs were standard general-purpose weapons. The guidance system was meteorology and mathematics. Anti-aircraft defenses became nearly useless. Japanese flak gunners calculated firing solutions based on where they saw the bombers. But the bombers weren't over the target when they released. They were miles upwind. By the time flak batteries opened fire, the bombers had already dropped their loads and turned away. The bombs drifted through airspace that wasn't being defended. Japanese fighter pilots faced similar problems. They'd vector toward bomber formations over the target, but the formations weren't there anymore. They'd already flown past and were departing. Interception became a guessing game. The operational statistics from April through August 1945 demonstrate the technique's effectiveness with brutal clarity. During that 5-month period, the 20th Air Force, which included all B-29 units, flew 414 missions against industrial targets in Japan. The average circular error probable across all missions was 1,050 feet. For missions specifically targeting oil refineries and related petroleum facilities, the average CEP was 820 feet. These accuracy levels matched or exceeded the best results achieved over Germany, despite flying at higher altitudes through more challenging weather conditions. The loss rates tell an equally important story. B-29 combat losses dropped from approximately 5% per mission in December 1944 to less than 2% per mission by May 1945. Part of this reduction came from weakened Japanese fighter defenses due to fuel shortages. But a significant factor was the backwards bombing technique itself. By releasing weapons while miles from the target and immediately turning away, bombers spent less time over defended areas. They were in and out before defenses could respond effectively. The tonnage dropped on Japan increased dramatically as tactics improved. In December 1944, B-29 units dropped approximately 1,400 tons of bombs on Japanese targets. By March 1945, that figure had increased to 13,000 tons. In July 1945, the last full month of the war, B-29 units dropped over 42,000 tons. The combination of improved accuracy and increased sortie rates meant the destructive power delivered to Japanese targets increased by over 30-fold in just 7 months. The oil refinery campaign's success led directly to the broader strategic bombing campaign against Japanese cities. Once LeMay had proven that B-29 seconds could hit precision targets reliably using backwards bombing, he had the credibility to propose area attacks using incendiary weapons. The firebombing campaign that began in March 1945 and ultimately destroyed over 60 Japanese cities was only possible because the precision campaign had demonstrated that B-29 seconds could deliver weapons accurately where intended. Individual stories from the crews who flew these missions reveal the human dimension of this technological innovation. Lieutenant William Standifer, a navigator with the 504th Bomb Group, flew 32 missions using backwards bombing techniques. His personal papers, donated to the National Museum of the Pacific War, include detailed notes on every mission. His entry for the March 27th mission against the Mitsubishi oil storage facility near Nagoya is particularly revealing. Today's mission demonstrated why backwards bombing works when nothing else will. Weather over the target was broken clouds at 20,000 feet. Using standard techniques, we'd have been bombing by radar with maybe 10% accuracy. Instead, we identified our release point 2.4 miles north of the target, using radar returns from the coastline. Released our load while flying at 290 miles per hour ground speed into a 180 mile per hour headwind. Calculated drift time was 62 seconds. Turned away immediately. Strike photos showed our bombs walked through the storage tanks in a perfect line. Every tank we were assigned to hit was destroyed. No wasted ordnance. No collateral damage outside the target area. This is precision bombing the way it was supposed to work all along. The technique's success also vindicated the enormous investment in the B-29 program. When the war started, critics questioned whether $3 billion for a single aircraft type was justified. The B-29's early missions, with their abysmal success rates, seemed to confirm those doubts. But once backwards bombing solved the accuracy problem, the B-29's unique capabilities became essential. Only the B-29 could fly high enough and far enough to employ this technique effectively. The pressurized cabin meant crews could operate at maximum efficiency during the long missions required. The range meant targets throughout Japan were accessible. The bomb load meant each successful mission delivered massive damage. By August 6, 1945, when the Enola Gay dropped the atomic bomb on Hiroshima, Japan's oil refining capacity had been reduced to approximately 4% of December 1944 levels. The 14 major refineries that had processed imported crude oil were destroyed. The smaller facilities that remained operational couldn't produce enough fuel to matter strategically. Japan's military was effectively immobilized by lack of fuel. Ships couldn't sortie. Aircraft couldn't fly. Training had ceased. Even if Japan had possessed the will to continue fighting, it lacked the physical means. The backwards bombing technique didn't end with World War II. It became foundational to strategic bombing doctrine during the Cold War. When the Air Force began planning nuclear strikes against the Soviet Union in the late 1940s, accuracy became existential. A conventional bomb that misses by half a mile just wastes resources. A nuclear weapon that misses by half a mile might hit the wrong city. Strategic Air Command invested heavily in meteorological research to understand high-altitude wind patterns worldwide. The goal was to identify release points where weapons could be dropped and drift onto targets using wind, the same principle as backwards bombing over Japan. The B-29 Superfortress, which entered service in 1955, incorporated backwards bombing calculations into its navigation and bombing systems. The AN/ASQ-38 bombing navigation system could measure winds at altitude, calculate drift, and determine release points automatically. Bombardiers could program the target coordinates, and the system would determine the optimal release point based on current wind conditions. The underlying physics were identical to Harold Jarrell's handwritten calculations from January 1945, just automated and computerized. Modern precision-guided munitions have seemingly made wind drift calculations obsolete. GPS-guided weapons correct their own flight paths regardless of wind, but the backwards bombing principle remains relevant in contested environments. When GPS is jammed or unavailable, you're back to the same problem American crews faced over Japan. How do you hit a target when high winds are pushing your weapons off course? The answer remains the same. Measure the wind, calculate the drift, release upwind of the target, and let physics do the work. The Air Force's current doctrine for GPS-denied environments includes sections on environmental weapons delivery, the modern term for using wind drift deliberately. Training programs teach pilots to calculate release points using wind data, the same mathematics that Harold Jarrell developed 80 years ago. The specific techniques have been refined and computerized, but the underlying principle remains unchanged. If you understand the physics and trust the calculations, you can turn environmental conditions into weapons. The human cost of developing this technique deserves acknowledgement. The missions flown between November 1944 and February 1945, before backwards bombing was implemented, suffered high loss rates and accomplished little. Crews died attacking targets they couldn't hit. The psychological toll of flying long missions through fighter defenses and flak, dropping tons of explosives, and achieving nothing was devastating. Some crews completed 10 or 15 missions without a single confirmed target hit. They watched their bombs scatter across Japanese landscapes and questioned whether their efforts mattered. The crews that finally made backwards bombing work operationally faced different pressures. They were pioneers testing techniques that contradicted everything they'd been taught. The first backwards bombing missions were flown by volunteers who understood they were experimenting with untested tactics. If the calculations were wrong, they'd waste their ordnance at best. At worst, they'd drop weapons on unintended areas and cause casualties among civilians. The crews trusted mathematics they couldn't verify until bombs exploded 60 seconds after release, miles from where they were flying. Technical Sergeant Robert Biggs, a radar operator with the 313th Wing, described the experience in a letter home dated March 5, 1945. The letter was preserved by his family and later donated to the mighty 8th Air Force Museum. Flying these backwards missions feels wrong every time. You fly past the target, see it disappear behind you, and then release your bombs into empty air. Everything in your brain says you just missed. Then you watch the bombs drift backward and impact exactly where they're supposed to. It's like magic, except it's just physics. But knowing the math is right doesn't make it feel less strange. After 20 missions doing this, I still get nervous at the release point. Still think we're making a mistake. Then the explosions light up exactly where we planned, and you remember that sometimes the counterintuitive answer is the right answer. The final statistics on Japan's oil refinery destruction are documented in the United States Strategic Bombing Survey, completed after the war. Of the 14 major oil refineries operating in Japan in December 1944, 13 were completely destroyed by August 1945. The 14th was damaged beyond repair. Total refining capacity dropped from approximately 2 million barrels per month to 75,000 barrels per month, a 96.3% reduction. This destruction was accomplished in approximately 5 months, using 342 B-29 sorties. The average accuracy across these missions was measured at 820 feet, circular error probable, far exceeding the accuracy of any previous strategic bombing campaign in history. The backwards bombing technique represents one of the most elegant solutions to a complex problem in military history. American bomber crews faced meteorological conditions that made standard bombing doctrine completely ineffective. Rather than accept failure or continue wasting resources on ineffective missions, they analyzed the problem systematically, identified the physical principles at work, and developed a counterintuitive solution that exploited those principles. The technique required trusting mathematics over instinct, accepting that the seemingly wrong approach was actually correct, and executing with precision under combat conditions. The oil refinery campaign's success demonstrates what happens when technological capability, tactical innovation, and strategic focus align. The B-29 provided the platform capable of reaching targets and delivering weapons accurately. Backwards bombing provided the tactical method to overcome meteorological challenges. The strategic focus on oil refineries identified the targets whose destruction would cripple Japan's war-making capacity. The combination produced results that shortened the war and saved lives. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.